I'm just going to give you an overview of how I go about interpreting radiometric data. Hopefully it can help you a little bit. Ask questions whenever you have a question. Let me just figure out why I'm not moving forward. Okay, so normally I must confess I hate talks. Not because I hate talks, but I don't like it to have a talk with I'm going to talk about this, and this. So, but it's the first time in a long time I'm using this slide. So, but I felt it would be good for you to see what we're planning to discuss. So I'm just going to shortly tell you what I think are the advantages and limitations of radiometric data. What types of rocks are potassium, thorium, and uranium most useful with. So I should say these are a combination of Stephanie and my sort of points that we thought would be good. How does the total count help? What is the workflow I follow when interpreting such data? Creation of ternary and ratio images to enhance the data. And examples of radiometric anomalies associated with different things like mineral deposit, lithological units, and then also just a quick example of using clustering methods to classify and interpret the data. So let's start at the top. What are the advantages of radiometric data? Well, and limitations. So the limitations are that it shows you basically what's at the surface. It doesn't really penetrate. I know you will read articles and things that say it can go down to 0.5 meter, but I doubt that. I think you just basically see what's on the surface, and of course the surface is not static. So if you're in the area like in the Northern Cape where you have a lot of sand cover, you don't know exactly where. If you don't know where the sand comes from, the anomaly might be associated with the sand, but the sand might be transported from a different place. So, but in other places, it might be just sand, just weathering material over a body, and it's actually related to what's underneath. So that's a bit of a problem with it. The advantages is it can give you nice compositional information. Say you have a granite outcrop, and it can tell you maybe where there's changes in the composition in terms of presence of the things that we can see, uranium, thorium, and potassium. Can also be used to detect alteration. So often when you have some sort of mineralization, you will have often potassic alteration. So that's what is often used for. And it can definitely, because it sort of maps what's at the surface, it can help to enhance geology maps. And geologists like it. I know here I have a colleague who does this serious clustering, makes this sort of in a complicated way, and she actually, when she gives her products to the geologists, they're always like, oh, this helps a lot, because, making a geology map, you don't visit every point in the field, you interpolate a lot. So when you have data that can help you with that, they're very happy with that. In my opinion, it's much easier to interpret than other geophysical data, like potential fields and EM. It's more straightforward. It's more sort of what you see is what you get. You don't have to worry about remnants or, all kinds of weird things. It has 3 bands. Okay, that's total counts as well, but say for potassium, uranium, thorium, which means you can use it to do cluster analysis to try and see where different radio element anomalies are and whether it's correlate and appear together. It has wide applications. It can be used with mapping, it can be used for mineral exploration, but also it's very nice for environmental studies. I'll show you some examples. So, okay, that was a quick introduction with that. So let's see what rock types are most useful. Will radiometrics be the most useful for? So these are as you can see, these are old papers, but I mean, the concept stays the same. So basically the radio element concentrations increase as you have increasing silica content. So you can see here, for example, let's take this line is potassium, the solid line. For the mafic, ultramafic rocks, there are very low concentrations of potassium. But as you go to the more silica-rich rocks, you get more increasing potassium. The same for uranium, and then especially for thorium. So, and here is just a table showing some values. So you have ultramafic rocks, you can see all the counts are very low, all the concentrations. But as you go up to more acidic rocks, they all increase. And the same with sedimentary. Basically, shales are mostly what you will see, I think, in the radiometrics. Some sandstones, but not things like dolomites really. And then metamorphic rocks also depends on, like the gneiss and schist. You can see stuff. But it doesn't mean you can't use it for ultramafic rocks. It's actually nice because you can distinguish between ultramafic rocks and felsic rocks. So if you look at this map, this is a ternary image. So we have potassium in red, uranium in blue, and thorium in green. And I don't know if you can remember from the theory, but the reason we don't say just uranium, but we say equivalent uranium, equivalent thorium, is that you don't measure directly uranium and thorium. You measure things from sort of other elements that you, now my words are escaping, but you get the concentrations from other elements. So,
Janine, can I just interrupt there? So, like, for example, I assume the data we've got is from CGS, and it said like uranium and thorium. So we immediately, like, nothing has to be done to the data. We immediately know it's equivalent to uranium, equivalent thorium.
Yeah, it's just people forget to use it. I'm just trying to be a bit pedantic. People normally will say, we will just say potassium, uranium, thorium, but technically it's not uranium. The value that what you have is the uranium, but it's equivalent uranium, but you don't have to do anything. You use it as is.
Okay, no, that's fine. That's good to know. Thank you.
Yeah, okay. So if you look at this map, you can see these dark areas. And immediately you can know where you have dark areas. There's a good chance, of course, you must look at your geology, but there's a good chance that it's mafic or ultramafic rocks. So if you're in an area where you have dolerite cells and things, or dolerite dikes, you can see them actually, or gabbros or whatever, you will see them on the radiometric data. It's just very dark areas. And then the lighter areas are where you have the felsic rocks. And I'm going to explain a bit about the ternary diagram. I'm going to show you also some more ternary diagrams, but it basically shows you it makes it obviously a three-color composite. So where you have areas that's red, here red means you have more potassium. We have areas that's cyan, means you have maybe less potassium, but you have sort of a mixture of thorium and uranium there. We have light colors, it means all the elements are high. Dark colors means all the elements are low. So that's just a very simple thing. So you can see lots of potassium-rich rocks here, and then other rocks that have all the elements in higher concentrations. And then on the right, when you have felsic rocks, you can go even further, and you can try to infer things about it, or just detect changes in composition. So this is a complex in Natal. Can't remember now the name, but you can see it's got high values, high counts, concentrations of all the things, but some have a little bit more cyan, which means there you have more thorium, uranium. Where it's redder, you have more potassium. Pink, you have potassium, uranium. So it's you just have to look at it in that way. So maybe we can then say a little bit more about this body. We can say maybe it's a granite or whatever, but we can say it can be, there might be changes in composition, there might be changes in cover material. You have to be careful, but you can add definitely more value to felsic rocks. The total count, that's always an interesting one, because I think we mostly use the separate radio elements, but the total count, remember, the total count measures the whole, I don't know, do you call this a spectrum? I don't know, but everything in here. Whereas potassium, uranium, and thorium, they just measure little sort of limited areas. So in total counts, you do have thorium, uranium, and potassium, but you also have maybe when there's other things, you won't know what it is. But if there's something that is not potassium, uranium, and thorium, but that's still radioactive, you can measure that. And interesting, quite a few years ago, we did a survey when we still radiometric surveys. And they flew over an area and there was an anomaly on the total count, but not on the others. And I can't remember what it turned out to be.
It's a radioactive source.
Yeah.
Some sort of industrial.
Oh yeah, it was a radioactive source for some industrial plant. So we could actually see it on the total count. So that was interesting. But in general, the total count is nice to give you an overview. It is because it uses the whole range. You have the most number of counts. So the image will be the clearest, the least noisy. So it gives you a nice overview of where there's radiometric stuff and so on. But of course, if you want more detail about what you're looking at, you will go to the individual elements. You can see on these images also, uranium is always very noisy because it's very low counts. So uranium always have these little, look very speckly. And then thorium is better, potassium is better. So I use total counts sort of as an overview thing, but I don't use it actively when I interpret. But that's just me. That's all I can say about the total counts. Okay, so what workflow do I use? So this is now what I do. So it doesn't say it's the only way. Also, I tend to use the grids, but I suspect it will be better to use the line data. If you have GSoft, you can look. If you want to focus in on an area, it will be good to look at the line data. But I tend to use the grids. So the first thing is you have to understand your aim. What are you looking for? Are you just helping with geology? Are you looking for a specific mineral deposit? For that, you need to know what are the characteristics of it. Is there some sort of alteration that's typical of it? Or if you're just looking for uranium deposits, then you can focus on the uranium channel. Are you looking for environmental things? So you have to obviously understand what you're looking for. Then it's a good idea to look at the geology and get an idea of what to expect. So you look at, when you write a report for an interpretation, you have like a section with a geological background. So now what I like to do when I do an interpretation is not, I'm not just saying, okay, there's Transvaal, dolomites of this and sandstone that belongs to this formation. I try to add the geophysical properties of. So if I'm doing a magnetic interpretation, I will say, okay, so we expect these rocks to be magnetic or whatever. So in radiometrics, it's the same. So I will say, okay, we've got, say, granites. Granites are typically have higher concentrations of radio elements. So then in my geological background, I will focus it more into a geophysical description. So because it's important to understand what you're looking at. You want to, if you have data, if you're going into a blind area where there's no data, then it's more difficult. But if you have an area where you know, okay, we have these granites, these sandstones, I expect sort of roughly to see this. Then if you see something different, you can immediately start to investigate and wonder what that is, if something doesn't make sense. But remember, geological maps are not perfect. Then I normally prepare all the images that I'm going to use. So those are the ternary images. I calculate ratios. I can show you, I'm showing you that as well. Also use a DTM because you're looking at what's at the surface. So if you have a valley that's full of sediments or something, it will affect the counts. So it's always important to use your DTM in combination with your radiometric data. Okay, so then I compare all the data that I've prepared with the geology, and I try to see, is it what I expected? Do I see additional information? So for example, for that intrusion or complex that I showed you earlier, I know there's a complex of some sort, but do I see more information about it? Is it maybe does it have different compositions or whatever in it? And then also identify areas of interest. Of course, if you do a mineral, if you're looking for a specific mineral target, you will focus on, do I see areas where there's maybe more potassium and so on. Or if you're just doing just a general map, help the geologists with their mapping, then you can identify areas that maybe they can go and focus on when they do their field work. And then you can do cluster analysis. The important thing is cluster analysis is just like an unsupervised classification. But the next step is you don't just do your classification, then you have to link it to the geology. So it also can be part of an interpretation. And then try to understand what you see. So if you interpret, don't just say, and you have an idea of the geology or whatever, don't say the thorium is higher than the potassium and so on. I mean, that's part of the interpretation, but now you have to add it. You have to add meaning to it. So you have to say, okay, all the elements are high in this area, so I think it's a granite. But if there's something weird, like there's some other body and suddenly there's an anomaly, then you have to try to understand or read up and find out what can explain why there's a high thorium anomaly where you're not expecting it. So that, our purpose is to add value in terms of from our data so that geologists and exploration people can use. Important thing is to involve a geologist. Although, we can read a lot of geology, normally the guys who go into the field, they know a lot. They can immediately see if you're on the wrong track or, what you're saying makes sense, or they can get excited about something. So it's always important to work together. So how to create ternary maps. So I'm just showing you, I'm using Pygmy, which is available. Oh, I forgot to put the link up, but it's free of charge. You just search in Google Earth for Pygmy, and there's Google Earth, not Google Earth, Google, and you will find it's on GitHub. There's a link to a Pygmy geophysical software.
Can I interrupt there? I've heard the developer of Pygmy is quite a cool guy.
No, he's quite nice.
Yeah, I've heard so. Everyone in the group, if you don't know, Patrick is also here. He's the developer. So if you've got any questions, he's more than willing to answer.
Yeah. So I'm showing you this view because this is in Pygmy how you create it, and then you can see the histograms as well. So this is an area in the Northern Cape. I'm not sure which area you are interpreting. I just happen to have done something in this around Uppington area. So this is obviously, so what you do is you put potassium in red, you put thorium in green, and you put uranium in blue. And there's a reason for that. It's not arbitrary. I read in a paper somewhere that because uranium is always very noisy, or likely to be the most noisy, if you put it in blue, your eye doesn't pick up the noise so much. It sort of gets buried in the image. So if you're going to put it in red, you're going to see it much, the noise a lot better. So this is sort of what we use. I just use two sort of different color bar things. This one I actually quite like. It shows you, they're both much of a muchness, but you must always just show which thing like this so people can know which channel went into which color. So you can see a lot of potassium rich sands and things, and then some more probably felsic rocks, granitic rocks, yellow when we got thorium and potassium. So yeah, so then that's I mean, you can play around with different combinations, but I would recommend this and try to stick to what you used to, because as you work, your eye gets used to a certain combination. So there's another type of ternary called the CMY, which is CMYK, cyan, magenta, yellow, and black. And if I look at that, there's an option in Pygmy to use that, but my brain just doesn't compute. I don't know what I'm looking at, but I'm so used to looking at an RGB ternary. But if I just look at it, I can get a feel. So just choose what you like and stick to it is my advice. Then there's another type of ternary that people have developed. It's a normalized ternary. So because thorium is a lot more abundant apparently, and from measurements they said it's about 4 times more abundant than the other elements of them. So they normalize the ternary image by doing the sum all the elements, but divide thorium by 4, and then each element gets divided by the sum, and thorium again by 4. It's in one of the papers that I will send. So this doesn't look as nice. And, the other image looks very nice, but in a way, it might show you more things. Or show things clearer. So if I go back to the previous image, we can see there's red sort of areas here, but it sort of gets a bit lost in the other other colors. So, but now that it's normalized, now you can see these things much clearer. And the colors seem to line up nicer with the normal color triangle that we use as a color bar. So now we see actually these things seem to be more thorium rich. It's not on the other one. It was sort of everything was high, but maybe it's sort of more thorium and uranium, not so much potassium. So I don't see people using it a lot in papers, but I think it can be helpful. It's not so nice, but it can be helpful. You can see actually some of the noise coming through as well. Then we do ratios. Ratios to show relatively more thorium than potassium, or more potassium than uranium, or less. And I'll show you why that is important just now. So one that's often used is this thorium over potassium. So we can see, so everywhere where it's blue, we have relative, compared to between the two, we have less thorium than potassium, but in these areas, we have more thorium than potassium. So it's straightforward to interpret, but it also adds some more information that you can use when you interpret. Then you get also things I don't often see, but it's also in one of the papers. I think it's the same paper or different, I don't know. Something called that somebody decided you can use these ratios also in ternary images. So you can make, for example, this is what then they call a potassium image. So in the red you have just a straight potassium channel, and then in green you have potassium over thorium ratio, and in blue potassium over uranium. And then it can give you more information. So you have to just then keep forget about what you're looking at now. So where it's maybe green, it means you have more potassium than thorium. So in these areas, that's also what we saw in the ratios. It's just a way of combining information to see if it enhances any little thing that you maybe couldn't see in any of the other images. Okay. So now I'm going quickly, so you must stop me from going too fast. I'm going to just show you some examples of in different applications. You can see what kind of things we do. So this is an area that's full of, this is all Transvaal sediments from the Transvaal group, the ternary image. And this is an interpretation. So here, I would say, I sort of did it manually here. Sometimes it's silly, I like to do things manually. So I sort of interpreted this map. And I did say, okay, this is high potassium, I describe it in terms of the radio elements, but you can also interpret like this area is slightly elevated. And maybe that's where the shell is altered due to more metamorphism of the dry-base intrusion. So this is sort of just a general interpretation map. So geologists can then take this, and when they do the mapping or they want to improve the geological map, they can use it. So, but try to add. Hello?
Sorry, Emily's next to me, so she's a bit noisy. I just wanted to ask you, when you make the image on the right, like, do you use Corel or Adobe or what do you do?
No, I use Arc.
Oh, okay, Arc. And so do you literally then draw polygons around the units?
I did, it's not clever.
That's what I would do. It must take you forever.
It can, yeah. This was not the hugest area in the world, but now if you do a big area, that's not really what you want to do. Then you want to do cluster analysis. But sometimes I get myself into these things, and then I can't get myself out of them because but it gets a bit difficult sometimes to then discriminate and whatever. But I thought I would share it.
Okay.
But you want to do classifications rather.
Okay, so I mean, But if you did it this
People-
way, you would get shape files out that you could then overlay on the magnetics, which would be great.
Yeah, yeah.
Okay. Okay. Thank you.
Classification, you can pick me, you'll get raster files, but you can convert into shape files if you want to
Okay. Cool.
in ARC. Okay. So this was a geological map. So then let's look at uranium. So this is an area in the West Rand, I think. We have uranium, we have gold mining, and as we know, in our gold mines, we have lots of uranium. So if I plot just the uranium channel over it, you can actually see, you can map the tailings dams, and you can also then use it to see if there's a stream, is some of the things coming of the uranium going into the stream. What is normally scary when you look at these uranium images over mining areas is you can actually often map built up areas, which is scary if you think about it. So this is just one, I'm just showing sort of one example of everything. So in terms of environmental problems, it's very useful for that. Of course, also the uranium, as I said earlier, if you're looking for uranium deposits, you will look at the uranium channel. More straightforward. But you can see, I mean, that's a road. So, and obviously also as the trucks drive and whatever, and wind blows, and bricks are made from some of the clay. Built up areas can look like little anomalies.
That's disturbing.
That is. And then now we come to the mineral targets. So why, this is where the ratio is very important. So say you see an area with high potassium. How do you know it's not just the geological unit that typically has high potassium, but it's potassic alteration. So potassic alteration. So there's where the ratio comes in. Thorium, if you have alteration, potassic alteration, you don't get thorium anomalies. Thorium doesn't increase at the same time as the potassium. So where areas where you have high potassium but low thorium, that might be an area of interest. So this is graphs from this guy's paper. So you can see, yeah, the potassium is high, and the thorium sort of lowish. That's where you would expect mineralization. And then the same on this side, the thorium stays low, but the potassium increases. And they have actually a value, I think, but I think it will depend on what you're looking at. Like if the ratio is 2.5 times 10 to the, because remember potassium is in percent and thorium and uranium are in parts per million. So it's 2.5 times 10 to the, I think, is it not 10 to the -4? Then you can say there's maybe mineralization. It's in the papers. So this is then what an example they did in an area, it's in Canada. So there's a known deposit. So you can see this is the potassium. So potassium is high. And then they did the thorium over potassium ratio, and that ratio is low because you don't have thorium in that area. And this is, if you look at the line data.
Can I ask, sorry, Janine, it's completely off the topic. Why is thorium and uranium parts per million and potassium percentage? Do you know? Because actually a student asked this when we were doing the presentations and I forgot to follow up about it. So I'm glad you answered it.
I think because potassium is so abundant in all elements, it's in all rocks because it's in feldspars and things.
Okay, yeah.
It's just a lot more of it. So although the normalization says thorium is abundant, but the thing is, I think if go right back to the start, sorry for this, go back in time, you can see sometimes thorium goes really berserk. But in reality, in the field, if you pick up a rock, you've got a better chance of having potassium in it than anything else.
Yeah,
that's what I think.
Okay, thank you.
That's my interpretation. Okay, so this is so this is for mineral targeting. Of course, when you do, as I said in the beginning, you have to know your aim, and then you'll do some literature study to see what have people done in other areas where they look for similar type of deposits, or what can you expect? Maybe there's something that has a different characteristic, not potassium, but maybe a different type of alteration that you can maybe see in something else. So it's important to not just diving. You have to know what you're looking for a little bit. And then this is again, I'm just showing from Pygmy. With clustering in it, you can do gives you all a few different options for types of clustering. But this was just, I did a straightforward k-means. So what I do is I use the terrain as well, potassium, uranium, and thorium. But then you have to normalize the data that you put in, because remember, the DTM will say you're 1,000 meters above, or the DTM values may range from 950 to 1,500, whereas potassium might range between 3 and 4 or whatever. So when you don't normalize your data so that they all go around, say, there's different options, but say around the mean with the standard deviation, we can make them range between 0 and 1, but they have to be normalized so that 1 doesn't dominate and bias, because you'll only see the terrain in the classification because the values are so big. Remember, it looks at the values. So you normalize the data so that they're all in the same value range. You put them into one multi-layer image and you do a cluster analysis. And then he has this scatter plot tool. So let me show you. There's the option in Pygmy, so you can do, say, k-means cluster. And you can decide how many classes it must find. So I just went, I said, okay, go from 5 to 8. You can put a minimum and maximum in. So I said, I want to see it from 5 to 8 clusters. So then it comes up with 4 maps. So it shows me this is what it would look like with 5 classes. So now we must try to link this to the geology. Then 6, 7. Obviously, as you go to a higher number of classes, you see more detail. For example, here in the top, in this one, class 1 is just this blue. But then if you go to 8 classes, you can see there's actually, it separates it into 2 classes there. So this is where you have to decide something you have to play with and see what gives you the most value and what you think, where you find it, when does it become ridiculous if you have like 20 classes? To interpret that will be a bit difficult. But what is nice is there's 2 scatter plot tools. So you can choose, for example, here I say we look at +5 clusters. And on the X, we have potassium, on the Y, we have thorium. This shows you the histograms then of thorium, of potassium on this and thorium. You can see, okay, so class 1 is where we have low potassium and we have low thorium. And then here we have, say, for example, here we have higher potassium, and there's really not much on the thorium histogram there. And what you can do is you can then draw in a polygon here, and on the right hand side, it will show you where this, say, if you draw in the polygon there, it will show you which classes it picks up on the right hand side. Or on the left hand side, you don't have to show the classes, you can say the amplitudes of the 2 whatever you're looking at. I'm looking for thorium, potassium again. So I see there's like a very high amplitude there. Obviously, it's where the histogram show we have the most counts. Then I outline that area, and on the right hand side, it shows me, oh, okay, that is where the classes that it's selected that corresponds to this. I hope that makes sense. You can select different areas here and it will show you which classes correspond to them, or on here. So it's just a tool to help you understand your classification image. I hope that makes sense. I hope it didn't confuse you now.
And then you said now you could export the different clusters as shape files or as rasters, you said?
As rasters, yeah.
Okay, cool.
Yeah. There's also a fuzzy clustering where you can actually then you can look at, becomes a bit more complicated. It can show, okay, probabilities. It gives you probability. So it will say, okay, maybe in this area it can be either this class or that class. You can play with it. But for a straightforward, easier thing, you can look at just a normal cluster analysis. And this k-means, I can't remember what the others that were there, but yeah.
that helps the obsessive compulsive who doesn't want to click just in case they're outlining the wrong area. So thank you, Beth.
Yeah. Okay, so that's basically my whole story. So just to summarize, there's no single way of interpreting data. And I'm sure if you use GeoShop and you use the line data and stuff, you can get a lot out of the data. Just when I started with it, we didn't really have GeoShops here. So then I got sort of stuck with doing rasters. But when you do, especially mineral exploration, then I would say go for the line data. Once you've highlighted an area, maybe from a region, from all the raster data, and you see an area of interest, go in and look at the line data, and you can get more information out. Try to understand what the data is telling you, and involve a geologist. They're quite useful from time to time. And these are just the references I have in the talk, but then I have some extra papers, also just a few extra. But I say they're a bit old, but I think they're still quite useful. So that is my quick and simple story.